Does it include underlying bits?
Well, maybe questions.
I saw someone say, yeah, sure.
Could be good, something with the discussion.
Yeah.
That's why we released all the parameters recently.
We're agnostic.
Sounds like a very open thing to the discussion. So let's now move on to finish up the session so that we can eventually get to coffee and other discussions. Now we have a talk by Nir Mandelker.
Nir Mandelker. Mandelker.
Simulated biological stability in galaxies.
Thank you very much. It's great to be back here in Santa Cruz. Always, it feels like home here, so I'm very happy to be able to be back here again. I'm going to pick up where Yicheng left off, continue the discussion about clumps, because that's one of our favorite topics here at UC Santa Cruz for the last 6 or 7 years. But I'm not going to be talking so much about how clumps that we see and their properties. I'm going to be spending most of this talk discussing about how clumps actually form in the first place from gravitational instabilities inside disks and what may trigger these gravitational instabilities. And if I have a few minutes at the end, I will say a few words about evolution of clumps, but my main issue is going to be on the formation of clumps. So we saw this slide in the previous talk. I just want to talk a bit about the global demographics of clumps. We see about 60% of star-forming galaxies at Z of 2 are observed to have these clumpy morphologies. This is from the Candles survey. Individual clumps can have masses anywhere between 10 to the 8 to 10 to the 9 solar masses. Their sizes can be anywhere from a few hundred parsecs up to about 1 kiloparsec for the largest ones. And if you look within a clumpy disk, then the clumps themselves can account for up to 20% of the star formation rate within that specific disk. So they're not a huge contributor to the global star formation rate of the universe, but they're an interesting enough minor perturbation that they're worth actually studying how they got there and how they evolved. I also just want to kind of like a flashy picture to show that it's not just the observations. Simulated galaxies at high redshift are also generically very clumpy, and they look very similar to the observations. These are 2 observations. These are 2 simulations. These are quite old. These simulations are from circa 2010, but they still look about the same as the observed clumps. This is a more modern simulation, which I'm now going to show you. Just kind of, I'm going to show you a film, because if a picture is worth 1,000 words, and a movie must be worth 1,000 pictures, and that's a lot of words. And this is actually taken from the Vela simulation suite, which we heard a bit about. And I'm going to show you the evolution from redshift 6 to redshift 4 of a certain star-forming disk. I want you to notice 2 things in this movie before I play it. The first thing, which is not directly related to my talk, but you can talk to me about it later, it's another thing that I study, is how these cold streams flow in toward the central galaxy, and they spin up the central galaxy and cause formation of the angular momentum and the growth of the disk. That's one thing you can notice. But the second thing, which is for our purposes here, is how the intense, very strong accretion onto the central disk galaxy induces what we call violent disk instability and the formation of all these very dense, very bound clumps that then slowly migrate toward the center where they coalesce with the central bulge. You can see this now begin to play. And so you can see the growth of the disk size and the disk angular momentum as it gets spun up by these streams. And you can see the very clumpy structure which forms on the outside where the streams hit the disk, and then the clumps begin to migrate and spiral in toward the center of the galaxy. As this simulation moves ahead in time, you begin to lose the planar structure of the 3 streams. That doesn't mean the streams actually have gone away. It just means that there's a central interaction region which grows and grows and grows until it's just well outside the 20 kiloparsec region that I'm showing you here. And it's the formation of a very nice clumpy disk galaxy by redshift of about 4. Okay, so that's the end. So where do these clumps come from? The common knowledge, at least for the past 10 years, if not even longer than that, is that these clumps form as a result of the Tourmaline instability. Since these galaxies at very high redshift are extremely dense and extremely gas-rich, the Tourmaline Q parameter, which has the surface density here at the bottom, drops well below 1. The disks become violently unstable, and they form these giant clumps. There was circumstantial evidence in support of this by these very nice observations by Reinhard Genzel in 2012, where he looks at a clumpy galaxy and he plots a map of the Tourmaline Q parameter, and he shows that in the regions where he sees clumps, which are highlighted here, the Q parameter is indeed well below unity, which suggests, according to this paper, that they formed due to a gravitational instability a la the Tourmaline instability. But some of you might be asking yourself, why is it justified to use a linear perturbation analysis, which leads to Tourmaline Q, for such highly nonlinear objects? Number one. Number two, the Q parameter was derived for an axisymmetric system. These disks are far from being axisymmetric. So it's at least worth studying in more detail using these zoom-in simulations to see if this picture indeed holds up. And I'm just going to give you the punchline. In simulations, the violent disk instability seems to deviate from linear Tourmaline instability. We see disks fragmenting in regions where the Q parameter is well above 3, which should be stable according to linear theory. So this suggests some kind of nonlinear instability that may be triggered by the intense accretion, as we saw, or by minor mergers or by major mergers. And just to show you visually what I mean by this, these are 4 examples, 4 snapshots from the Vila simulation suite. This is the surface density of gas, the surface density of gas. And what I'm showing here and here is a 2-component Q parameter where we account separately for the gas and the stars. And what you can see is that it's true that where the clumps themselves are located, Q is indeed quite small. It can be, can be far less than 1, but that's a meaningless statement because where the clumps already exist, they're nonlinear objects. The surface densities are huge, so clearly Q is going to be very small, but that doesn't mean anything. If you look in between the clumps in most of the disk, you see Q that, in this case, it's Q anywhere between 2 to 5, between 5 to 10. This is okay, Q around 2. Now, some of you might be asking yourself, well, okay, fine. So a lot of the regions in between the clumps have high Q, but surely the clumps themselves, where they form, locally, Q is going to be small even before the clump formation. That's a fair point. That's why I'm going to show you this histogram, which is looking at Q specifically in the regions that are about to form clumps, the proto-clump regions. Now, how do I do this? I have a clump finder, so I can find a clump in a given snapshot. Then I can trace that clump. I can trace it back through time until just before it forms. And then I can measure Q in that proto-clump region just before it forms. And I still find that Q in those proto-clump regions can be well above 2 in a lot of cases. This is from a paper led by Shigeki Inoue back about 1 year ago in collaboration with Avishai Deckel as well. So just to show you kind of in a few snapshots how this happens, I've highlighted here the region that's about to form a clump, a proto-clump. This is the surface density of the baryons. And so again, that kind of 2-component Q, where here in this region, Q is above 3. And as you take it forward in time, you can see the clump beginning to collapse. And sure, once the clump is collapsed, Q is well below unity, but again, that doesn't mean anything, okay? Where we started out, Q is above 3. So how can we explain this? Well, one idea that we had has to do with something called compressive turbulence, which I'm going to now take a couple of minutes to explain to you what I mean by that and why we think this might help. Okay, so if you take just a random velocity field and you circle a certain patch, so this is the velocity at the center of that patch, it's the constant vector field. If I subtract that off, I can get a linear residual and a nonlinear residual. Let's focus on the linear term for the moment. This can be divided into 3 separate terms. One term that represents compression and expansion around the central point. This has 0 curl and it has the entirety of the divergence. A second term, which is basically solid body rotation about the central point, that has 0 divergence and contains the entirety of the curl. And the third point represents shearing motions around the central point. It has both 0 divergence and also 0 curl. If you take these 3 components, this component is often known as the compressive mode of the velocity field, And these two components can be grouped together and called the solenoidal component of the velocity field. Now, for a velocity field that is in equipartition, the solenoidal mode contains twice as much power as the compressive mode, because compressive motions are in 1D, whereas solenoidal motions are in 2D. So just by a simple equipartition argument, you get twice as much power in solenoidal motions as you do in compressive motions. Now, when I put sigma in my Q parameter, I'm kind of assuming that there's an equipartition, so I'm assuming this ratio of the power between solenoidal and compressive motions. But if for some reason, at least locally, compressive motions were dominant, then I could get a very high sigma, which would lead me to a very high Q, but that doesn't mean that my disk is gravitationally stable. Because if most of what I call sigma is induced by motions like this, and not going to be stable, it's actually going to promote the collapse of the region. Now, just to show you how that situation in principle could happen, so this is taken from a major merger simulation by Renaud and Bourneau et al. And what they found in this major merger simulation was that around the time of the first of the pericentric passage, the fraction of gas mass which was experiencing a compressive tidal force spiked. Okay, and when that happened, it caused the ratio of the compressive modes to solenoidal modes to flip. Before the merger, it was that same 2-to-1 ratio in favor of solenoidal modes. But when you have the compressive, when you have the compressive, you have the forces, the compressive mode actually began to dominate, and that led to a burst in star formation in the disk. So we're dealing with these very high redshift galaxies. We saw you had intense accretion, you have lots of mergers, minor mergers, you have major mergers. We wanted to know, does a similar scenario work to explain the motions in these high redshift violently unstable disks? So globally, the answer is not really. Okay, this is just one example where this is taken from the Vela simulation suite, one of the examples that I showed you. I'm showing you as a function of time, the cosmic expansion factor, the fraction of the energy in solenoidal motions versus compressive motions. So the sum of the blue line and the red line is equal to 1. And you can see that it doesn't matter if I weight by volume or if I weight by mass. Globally, if I take the average on the whole disk volume, you still have the 2/3 to 1/3. You could argue that maybe I have a 10% effect here, where the solenoidal motions are globally 10% lower than expected, but that's not very interesting. Okay? The only real difference between the volume weighting and the mass weighting, I should add, is if I divide the compressive mode into modes that are either converging with a negative divergence or expanding with a positive divergence, then that does look very different if you volume weight or if you mass weight. But just the 2/3 to 1/3 globally does seem to hold. But what about locally? So I'm now showing you the same sequence of images of the clump that was forming out of a region with high Q that we showed you just a moment ago. Only now, so this is again the surface density of the gas, but now I'm showing you the ratio of converging flows, compressive flows with negative divergence, to the total power. And you can see that that region, which had a very high Q that was above 3, that began to form the clump, has a very high ratio of converging to total motions, above 0.6. And as I take that through time, you can see that as the clump forms, this ratio stays high until the clump is there, at which point that ratio drops very dramatically. There are 2 reasons for that. Number 1 is the clumps, we know, have very strong outflows. So if I'm limiting myself here to converging flows, in this case, I can be dominated by flows that have a positive divergence because of the outflows. And the second thing is that we know that after the clump has collapsed, it begins to rotate about its center of mass, and that contributes to the solenoidal mode of the turbulence. Now, statistically, if I go and I look at all my protoclump regions, like I did when I was showing you about the Tourmalet Q, if I look in the regions of the protoclumps, I can see that we have ratio of compressive to total motions that are quite high, well above 1/3. Now again, this is only with a negative divergence, so it's half the total compressive motions, but would expect it to have a peak at about 1/6. But it has a tail to extremely high values. And the red histogram is looking not in protoclump regions, but in a different part of the disk in the same radius. and that has much lower values. Now, some of you might be thinking, Nir, isn't this a self-fulfilling prophecy? Because if I'm looking in regions that are about to collapse, okay, fine, they haven't yet collapsed, but they're about to collapse, surely by construction, that means that I'm going to be biased toward converging flows. And we thought of that's a good point. It's a good point. So what we did was we took an isolated simulation, a non-cosmological simulation that was run by Frédéric Bourneau, and we ran exactly the same experiment. We found all the clumps, and we looked at the ratio of compressive to solenoidal modes, and this is dramatically different. Okay, the disk does seem to be an equipartition, and unfortunately I don't have the histogram here, but if I look at the Tourmaire Q parameter in the protoclumps in the protoclumps of this simulation, they're basically as expected. Q is about 1. So this is very different. This is markedly different. And now just to summarize this part, so we said that high redshift, very massive disk galaxies are violently unstable. We have that massive clumps seem to form in regions that should be linearly stable, where Q can be even above 3. Clump formation seems to be associated in cosmological simulations with compressive flows that is not seen in isolated disk simulations. Now, the open questions, which we're still working to kind of, really complete the discussion, is what exactly causes compressive modes to dominate. Is it the intense accretion that we talked about? Is it minor mergers? Is it major mergers? Is it clumps that are there in the disk that induce compressive motions in their wake? Do compressive modes lead to clumpy disks? The clumpy disks lead to compressive modes? What's the chicken? What's the egg? Do we have stimulated formation of new clumps in the wake of clumps that are there? And if we try to modify the Tourmaire Q parameter to only account for the solenoidal component of the turbulence, is that going to be a better measure of disk instability than the kind of traditional Q, which uses the entirety of the velocity field? Now, how much time do I have? Like 1 minute? All right, I'm going to use that 1 minute, and I'm going to briefly give an advertisement to another project that we're doing. You can talk to me later if you want to hear more details. We heard from Yi Cheng in his talk about the 2 different models for clump lifetimes. Are clumps short-lived or are clumps long-lived, and how we can use the longevity of clumps to constrain models of the feedback. So I'm not going to go into the details here. I just want to say that in a paper together with Avishai Deckel and Frédéric Bourneau, we've come up with an analytical model for the evolution of the properties of clumps in the scenario where they're long-lived and they're bound. And this can be extremely handy to compare with observations in order to, it's good to have not just a simulation, but a real analytic model to compare to the observations. The model accounts for accretion of gas onto the clump from the disk, and it accounts for outflows induced by feedback. It accounts for star formation, and it accounts for the tidal stripping of stars, and it also accounts for stellar mass loss. I don't have time to go through the details. There are 4 parameters of the model that determine the strength of the accretion, the strength of the star formation rate, the strength of the outflows, and the strength of the tidal stripping. I'm going to skip this. I'm just going to show you. You can talk to me about this. I just want to show you how the model compares to simulations and to observations. So the black curves are stacked results from the Vela simulations. The red curves are the results of the toy model for very reasonable set of parameters. Again, there are 4 parameters, and I'm simultaneously fitting star formation rate, mass, the gas fraction, the specific star formation rate, and depletion time. And it works quite well. And if I compare to the observations that we just heard about from Yi Cheng from his catalog, with the same set of the parameters that fit the simulations, they fit very well the observations from Yi Cheng. So this really is a useful tool to use to study the evolution of clumps using an analytical way. You can talk to either me or to Avishai if you want to hear more details, and I'll end there. Thank you very much.
Thank you. So we have time for one question.
What about if you separate the dispersion within the plane and out of the plane?
So sigma R versus sigma Z. So in the Tourmaire criterion, we only put in the radial component of the velocity dispersion. So in some sense, we are already separating that out. Where sigma z does come in is in what they call the thickness correction to the tumor IQ. So that is included in that way, but we only include the radial component. That's a good question. I don't know the answer to that yet. I haven't looked at the compressive and solenoidal modes, how isotropic or anisotropic they are. That's a good question. I should look at that.
Okay, so at this point, let's give a round of applause to Nir and to all the speakers in the session. And quickly, and then Joe will have an announcement.
So just a brief announcement. You may have noticed that there's a big sign on the door to this room on the outside that no food or drink is allowed in here. We're guests of the University of California, Santa Cruz Engineering Department. This is their room. And they will throw us out if they discover that many people are bringing drinks and food into the room.